to too much, but sometimes we do. I'm going to teach it like you don't know it. So, first of all, rational graphs look pretty funny. Sometimes they're just like in two different parts like this. Sometimes there's like three different parts. You might have like something like that and then something like that in the middle. So there's definitely a twist with them. They have vertical asymptotes and horizontal asymptotes, which is the first thing we're going to figure out how to find where those are. So a rational function is something that has a polynomial in the numerator and a polynomial containing an x in the denominator. The denominator has to contain an x. The numerator doesn't necessarily. Like if you look at example B, obviously the numerator is just a number. But the denominator has to contain an x, which is what makes it rational. The domain is always going to be all real numbers with a couple exceptions based on wherever your vertical asymptotes are. And vertical asymptotes come from the denominator. So any place where the denominator would equal 0, that number has to be excluded. So the easiest way to find your domain is to take your denominator and just say that it cannot equal 0 and solve that. So subtract 5 from both sides and x cannot equal negative 5. It can be all real numbers except that. On the next one, x squared minus 4 cannot equal 0. You can either factor this or you can just isolate. So x squared cannot equal 4. Square root of both sides will say x cannot equal plus or minus 2. C is not a rational equation at all. C is technical, so there is no limitation to your domain. It's all real numbers. C is technically negative 1/3 x squared plus 2/3, which is a what? It's not a linear function. It's not a rational function. It's a quadratic function. So that really doesn't apply. The domain would be all real numbers. And then on D, D is rational, but I don't believe we have any exclusions. Because if you set up this so that x squared plus 1 cannot equal 0, you don't really have any places where that happens anyway, because you can't take the square root of a negative number. So x on this one can also be all real numbers. Anytime you square something, it's going to be positive, or at the very least, it'll be 0. And then you add 1 to it, and you don't have to worry about that ever equaling 0. So, your vertical asymptotes, we're not really there yet because this is asking about domain, but you're going to have a vertical asymptote at negative 5 on this graph. You're going to have two vertical asymptotes on this graph, one at positive 2, one at negative 2. Element of. That symbol means is an element of. It just means that x is in the real number system. So x can be any real number. The real number system is like a set. So this is saying that x is an element of the set of real numbers. No. If I gave you a set, like a set of numbers like 2, 4, 6, and 8, a set of numbers is just like a list of numbers. And this is the set of any real number. So there's an infinite kind of list there. But I would just say that 4 is an element of this set. If I call this set A, I'd say 4 is an element of A. Sure. Have you never seen that symbol before? No.
I've seen like the E on the calculator.
No.
I never.
Okay, good to know. So it looks like a C, but like with a little line in between that means
So
is an
it
element
mean?
of.
What does that mean?
It means it's an element of.
Yeah.
It means it's an item within it. So like I could write like golden retrievers are an element of the set of dogs. You know? It's nothing to get worked up over, but I'm glad that you mentioned it. Okay, so your denominator essentially tells you about your vertical asymptotes and about your domain, I should say. Your x-intercepts come from your numerator. So whenever the numerator equals 0, right? X-intercept is when the function equals 0. The function's only going to equal 0 if the numerator equals 0. The y-intercept, like any other function, is when you set x equal to 0. So that's what the value of f of 0 is. And so down below here we'll find the x-intercepts and the y-intercepts. So again, the x-intercept is just whenever the numerator equals 0. So the x-intercept, what would x have to be for the numerator to be 0? 0. The y-intercept comes from actually plugging in an x value of 0, which would be 0 over 0 squared minus 4, which is just 0 also. You guys knew that, right? Like that if ever the x-intercept is 0, then the y-intercept has to be 0 and vice versa. You can't be a y-intercept of 0 without also being an x-intercept of 0 and vice versa. On B, the x-intercept comes from setting the numerator equal to 0 in solving. So the x-intercept is -3, which means this graph would cross over there someplace. And the y-intercept would be whenever x is 0, so 0 plus 3 over 0 minus 1, so 3 over -1, -3. That's very little information for the whole shape of the graph, but critical points that when you're graphing need to be accurate. Okay, and then more on vertical asymptotes. So our domain came straight from the denominator, and our vertical asymptotes are too, but you have to simplify it first, which is what this first phrase is saying. A rational function in lowest terms. So once you have it in lowest terms, whatever kind of zeros of your denominator still exist will be vertical asymptotes. So if you look back up at the top, these all already were in simplest form. So we were able to say, okay, our asymptote is at -5. Our asymptotes are at plus or minus 2. Some of these down below, D mainly, are not yet in simplest form. So we'll get there. But when you factor out and try to get these in simplest form, nothing really cancels on this first one. So your vertical asymptotes are still at -2 and +2. Mike, where do you think your vertical asymptotes are for B? Not the -3. -3 is coming from your numerator. So -3 is a root. It's an x-intercept, whatever you want to call it, just from the denominator. Just the one, yeah. C doesn't have any, because this will never equal 0. And then D, we have to factor out both the numerator and the denominator first. And see, what happens here is that your x minus 3's will cancel. That's going to lead to a key feature. It's just not going to be a vertical asymptote. So because those cancel, The vertical asymptote is only where, Brock? -7. Horizontal asymptotes is the really new thing. It's totally brand new to you, and you have to pretty much memorize these 3 rules right here. So you guys all know that a vertical asymptote kind of blocks out that value from the graph. So the graph will never cross a vertical asymptote. Horizontal asymptotes, however, can be crossed. Horizontal asymptotes have a different, sometimes they're not crossed, that part's true, but they have a different purpose. The purpose of horizontal asymptotes is to guide the end behavior of a graph. So, something with horizontal and vertical asymptotes, again, we'll never cross the vertical asymptote, so that's just going to go up. But as you get towards your end behavior, this graph just gets closer and closer to that horizontal asymptote, which is kind of how verticals work. But you can also cross horizontal. So if I were to do something on this side, like this could happen, where you'll never cross your vertical asymptote, but you can cross your horizontal. Most importantly is when you go towards an x infinity or negative infinity, it will get closer and closer to your horizontal asymptote in that direction. Does that make sense? So here are the rules to figure out your horizontal asymptote. The rules are, it's totally, where the horizontal asymptotes are totally based on the degree of the numerator and how it compares to the degree of the denominator. So if the degree of the numerator is less than the denominator, then the values of our x approach 0, meaning essentially that the horizontal asymptote is y equals 0. If the degree of the numerator and the denominator are the same, then the horizontal asymptote just comes from whatever their coefficients are. I'm going to give you better examples. This makes it wordier than it has to be. If the degree of the numerator is greater than the degree of the denominator, then there is a slant asymptote. So here's really the way I would teach this and write the notes. If it's small over big, as far as the degree is concerned, small over big means y equals 0 is your horizontal asymptote. If it's big over small, there's no horizontal asymptote, and in place of that, what guides your end behavior are called slant asymptotes, which means something that's not a horizontal line. Could be a diagonal line that guides your end behavior, could be a quadratic shape that guides your end behavior, but it's not a horizontal line. And if it's same over same, it comes from coefficient, leading coefficient, I should say, over coefficient. Can you pick one from those 4 examples that would qualify as same over same, and then I'll show you what that means? B. You see how B has a degree of 2 up top and a degree of 2 on the bottom? So your slant asymptote, or your horizontal asymptote is just y equals 8 over 4. You just take those leading coefficients and divide them. It's just 2. Yep. Yep, C is also degree of 1 over degree of 1. So your coefficients are what over what? 1 over 3. Good. Sure. So this is obviously a horizontal line, y equals 0. This is going to be y equals some number, whatever the fraction makes. So that's a horizontal. Anytime you have y equals a number, that's a horizontal line. The big over small case will not be horizontal. It'll be some other diagonal line or shape. So here's B, just for the sake of showing you the picture of it. And we'll get to graphing these by hand, but we're starting with the features. Your see how it, like, as you go towards infinity and as you go towards negative infinity, it kind of flattens out? That's happening at 2. Yes? Other features that we've talked about are x-intercepts is when, well, this one would require some, is it factorable? Is that numerator factorable? 4x and 2x. 1 and 2. I don't think it is. There are two numbers that multiply to get 16 and add to get -1. No. So it's not factorable. So your x-intercepts are going to be wherever the numerator equals 0. So you'd find those by doing 8x squared minus x plus 2 and figuring out where that equals 0. Which, if it's not factorable, how do you have to solve that? Quadratic formula. So negative b is 1. B squared is 64 minus 4ac all over 2a. So that's a discriminant of what? 64. B squared. Oh, I don't know. You're right. I made a mistake. Oh, good. B squared is 1. 1 minus 4 AC. So this is imaginary, right? It's a negative number. Negative 63. Doesn't matter. They're imaginary. So you have no x-intercepts. And if you look at this graph, something's happening down here, but it's definitely not getting high enough to cross the x-axis. So that kind of matches up with why we have no x-intercept. Our y-intercept is when x equals 0. So we just have to plug that in. So that's 0 minus 0 plus 2. And 0 minus 1. So we have a y-intercept at -2, which maybe I need to zoom more so you can see that, but if I go like -4 to 4. Yeah, see, you can see it crossing the y-intercept at -2. What other features do we talk about? Vertical asymptotes, right? So if vertical asymptotes come from your denominator. So that does factor into 2x plus 1, 2x minus 1. So your vertical asymptotes are at -1/2 and +1/2. Yes? And you can see that you have two vertical asymptotes, one that would go right in there, and another one that would slip right in there. That's it. That's really your main features. 2x plus 1, 2x minus 1. No, if you immediately teed it up, you'd have to take the square root of 1/4 on both sides, which would be plus or minus 1/2. Yeah. So we'll eventually bring all this together and have to do all that, but right now we'll go back to horizontal asymptotes. So those were both same over same. This one is big over small or small over big? Small over big. So this one will just be y equals 0. And plus x plus 1. That one looks like this. So again, you can see as you go further in that direction, you're just approaching 0 on both sides. That's your horizontal asymptote. And this one will be more interesting because it's big over small, so there's no horizontal asymptote. You'll see that this graph, when I show it to you, is not going to flatten and be like a horizontal line on either end because of that lack of horizontal asymptote. Instead, it's going to, it has end behavior. I'll tell you, this end behavior is getting closer to some diagonal line. If I even open this up even a tiny bit, I think I should be able to see whatever the diagonal line is that's going to kind of thread the needle right through there. That's what your slant asymptote is going to be. So it's still guiding your end behavior, and as we go towards an x, if we let x go towards infinity, it approaches that diagonal slant asymptote. It's just not horizontal. And we'll be able to find the equation of that eventually, but we'll leave that off for today, not to complicate things. But long division will come back into things. I thought you liked long division, Allie. No, not at all.